Hello everybody. Now we are going to solve a couple of problems on the Ergen equation and see how we can use it to calculate the pressure drop for packed beds. So the example we have here is for water. We know of course the density and the viscosity of water that flows through a horizontal duct that has a rectangular cross-sectional area as we see here. And the area is 0.2 times 0.1 meter square, and the mass flow rate is 2 kilograms per second, and the duct is packed with 9 million small cylinders. So this is the shape of the particle of the packing in the bed, and it has a diameter of 1 millimeter and length of 2 millimeters. So each one of these cylinders has diameter of 1 millimeter and length of 2 millimeters. Oops, I'm sorry. And we want to calculate the pressure drop per unit length of the duct. So I put here all the information that we have, the equation that we use for the pressure drop, the mass flow rate, the density, the viscosity, the area, which is length times width, the length of the duct, and the number of cylinders, the diameter, and the length of these cylinders. Just one thing before we proceed. This equation is the one that we were discussing last time, if you remember, and the one that we said that we use for, so this was the general form. And we said that if this term for delta Z, if it's a gas flow or a horizontal pipe, this term will be negligible. So that's why we used this case, because we have a horizontal duct in this problem that we have here. So the only thing we want to do now is to calculate the missing parts here, or the missing terms here. So we know the density, the viscosity, we know the length of the pipe, we don't know the particle diameter, we don't know the superficial velocity, and we don't know the porosity. So if we can calculate these three parameters, we will be able to substitute and calculate the pressure drop. So we are going to go one by one. So for the particle diameter, it has to be calculated from the specific surface area, which is area over the volume of one particle. So the area of one particle is the total external surface area. So it's a cylinder, so it has the cylindrical part, and it has an area from this side and from this side. So it has two circles and the outer cylindrical surface. So it's 2 times pi over 4d square plus pi dl over the volume, which is the area, times the parameter, the length, which is pi over 4d square times l. With some simplification, we can reduce or cancel the pi. We can cancel the d square. Here we have the square. We can cancel the square with the diameter and the diameter. So it can be in this more simpler form. And by substitution, we can calculate the specific area or surface area of a particle, and the particle diameter is, or the effective particle diameter is 6 over the specific surface area. So this is the first term that we didn't know how to calculate. So we are done with this. Now let's calculate the porosity. So for the porosity, as we said before, it's 1 minus the volume of solids over the volume of the bed. So the volume of the bed is very easy. It's the length, width times height. So it's this area 0.02 times 1, so it's going to be 0.02 meter cube. The volume of the solids is the volume of one particle times the number of particles. So it's going to be the number of cylinders times pi over 4d square L. And this is 9 million times the area, so it's 0.014 meter cube. So now we know the volume of solids, we know the volume of the bed, so we can calculate the volume of, or the porosity, or the void fraction, which is 1 minus the solids volume over the bed volume, so it's 0.293. So now we're done with these two parameters. The only missing parameter now is U node, which is very simple. U node is the superficial velocity, which is the velocity based on the total cross-sectional area. So it's the mass flow rate is already known. So it's mass flow rate over A rho. So by substitution we can calculate U node, and the rest is just direct substitution in the equation, and we can calculate the pressure drop. So it's very simple and straightforward. There's just one thing to notice here, that the pressure drop is 6 atmosphere, and 6 atmosphere in a pipe flow, if it's just a normal pipe flow without any packing or any solid particles, it's very hard to reach this very high pressure drop in short pipe length. This is only 1 meter pipe. This is 1 meter pipe, and the pressure drop is 6 atmosphere, which is a lot. And this is what we expect from the flow through packed beds, that the pressure drop through the solids is higher than much higher than the flow in empty pipes or tubes. So for the second example, we have a large tank that is filled with water. There is some information in the figure that are not in the text. So it says that the tank drains water by gravity through a pipe, an exit pipe of diameter 1 meter. So this pipe has diameter of 1 meter, and it's connected to this very large tank that's 100 meters long tank, and this pipe is 20 meters, and this 100 meters tank is height tank is filled with water. And in this tube there are sand particles that have uniform average diameter of 0.2 millimeter. So this is the diameter of particles here. So they are spherical particles, which is they have the same, and we can consider them all to have the same diameter, which is 0.2 millimeter, and the void fraction is 0.3. So we are given the particle diameter and the void fraction, which is good news. And this is water, so we know the density and the viscosity, and this is the diameter of the pipe, and we know the length of the pipe is 20 meters as well. So this is where the flow through the solid particles is. This is, you can consider this as a sand filter. It's used to remove solids or any suspended solid particles from water. Anyway, so we want to calculate the volumetric flow rate of water through this column. So we can start by applying Bernoulli equation between points 1 and point 2. So point 2 is, as it says here, it exits to the atmosphere, and this large tank is open to the atmosphere. So if we apply Bernoulli equation between these 2 points, we can find out that the pressure here is atmospheric. This pressure here is atmospheric plus rho gh. So what is above can be considered static fluid. So we know P1 and P2. And we know that this is the diameter here and here are the same, so the velocities are equal. And the height here is 0, and this is 20. And as I said, the pressure is atmospheric plus rho gh. Here is atmospheric only. So by substitution, we will calculate everything except HL. So we can find HL from the substitution in the rest of the terms. And now we know the head losses. Now we want to use this information to calculate the flow rate of water in the pipe. So to calculate the flow rate, we can use the equation of losses, which is Ergun equation. And here we need to check if we are missing anything. We know the porosity, we know the particle diameter, we know the viscosity, we know the length, we know the or we want to calculate the superficial velocity. So we can substitute directly in the equation with all the variables that we have, and we will have here U node, and we'll have U node power 2. So it's a second order polynomial equation in U node, which can be solved with many methods. You can use a calculator, you can do the use computer software, or we can use the formula, which is negative b plus or minus root b squared minus 4ac over 2a. And from this we can find the roots. So we have 2 roots. This is one which is 8.622 times 10 power minus 4 meter per second, and there is one that's negative. Of course, the negative is not accepted, so we will accept this as the right answer. And from this we can multiply this velocity by the cross-sectional area, which is pi over 4 times 1 power 2, which is the diameter. And from this we can calculate the volumetric flow rate, which we can convert into gallons per minute. as we see here. So this is this is the second problem. So I hope this made the equations clear and easier to understand. So we'll stop here, and the next video inshallah we are going to start with the second part of this chapter, which is the fluidized beds. So I'll see you then inshallah. Goodbye.